All right, everyone. Last day of the first week. So, what do you think of the video? Is it okay? I put it on YouTube. It's 400 megabytes. I wasn't able to bring it down to a reasonable size. I think that's reasonable, but I wanted to do something less. But that camcorder is super high quality, and I don't know how to bring it down. I think that's the lowest. So it's a little bit of conversion, but I think it's good to have videos. You have any questions before we start? We're going to refresh kinematics today. Yes?
After registering for SDK,
yes.
What exactly is the registration ID and the...
You have to follow those 5 bullet points that I put on the PDF, either on my website or on Canvas. So you go to that link, go at the bottom of the page. There is a big blue button that says download SDK 10. You install it. Then you don't have to open SDK. What that does is installs the program and also something that is called the license manager. You open the license manager. That shows you 2 numbers. That's what you have to send Patrick so that he can go into the AGI's website and request a license for you, which I get via email and I send to you. I know it's a long procedure, but that's what I have to do.
When
yes?
you say open the license manager, it doesn't get installed. So there's a separate...
It should. I've done it a few days ago, and it should install the whole thing. So when you, I don't know if you have Windows 8, for example, just go into searching your programs and start typing license, and it should show up, license manager. It has the same icon that SDK does, and that should be it. Yes?
The other question I have is for certification.
Yeah.
Other steps are we supposed to do to start?
So this is stuff that we discussed at office hours.
Okay.
Yeah. So I think, everybody's excited about these extra points, but I'm telling you, this is not something you do in a day. So don't get too excited because it is extra work. And so if you want to do it, it's good to get ready now, but this is not required for the class. I hope it's clear. It's an additional project. So you come talk to me at office hours. Don't get distracted by this the whole time. Okay? So it's something that you want to start now, but it's going to take a few weeks at least, especially if you take it more than one class. All right, so we need to start kinematics here today. And I will try to compress as much as possible. I think this is too small for everybody, right? Okay, just checking. Probably I was writing the same size last time. Kinematics is the way, it's a way to, it's what we do to represent motion. We don't understand why things happen, but we can represent them. So the ingredients that we need are E3, which we mentioned last time, Euclidean 3D space. This is a very precise mathematical definition, which we don't have to really go through, but that's the way we try to represent this volume we're moving in and the space planets move in. So this E3 comes with some properties, the ability to measure distances from a point to another, and so on and so forth. And so we want to see how objects move in this space. Now, when you look at an object and you want to say, that's its position, that's its velocity, that's its acceleration, what do you use? Use vectors. So that's second ingredient is vectors. Now, this is, I do it always. This is not a vector. I don't care what MATLAB tells you, this is not a vector because these are 3 numbers. There is no basis here. This means absolutely nothing without a basis. A vector is, let me write it here, is an object with magnitude and direction in E3. And by object, I mean object. Like if I'm talking about this table. So this is my vector, and it's here. It exists regardless of whether I'm looking at it from here, from behind, from down there. It's an object that exists in 3D. That's something that we define and we use to represent positions, velocities, and so on and so forth. So 3 numbers don't really mean anything by themselves. Now, what do we represent with this? I think it's good to list all these things. It's positions to begin with. And then if we really want to do kinematics, we need to be able to compute velocities. and then accelerations. We have to go all the way down to accelerations. Why? Well, because in mechanics, in dynamics, what you want to end up being able to do is apply, for example, for a particle, what is called Newton's second law, which we're going to see next time. So this is a refresher of dynamics that goes pretty quick, but I just want to touch on the key points. So the fact that you want to define positions and then take the rate of change of positions and then take it again and find accelerations is because to find the equations of motion that originate from an equation like this, you need to be able to compute this side to begin with. And n here represents an inertial reference frame. I haven't defined a reference frame yet, and I haven't defined what inertial means, but we'll do it. But the bottom line is that you need to be able to compute accelerations of particles with respect to some observer. So I'm already using a lot of words here that we haven't really defined. Reference frame, inertial, observer. We're going to try to do that today. But again, you need to be able to solve for the right-hand side of this equation first. And then in kinetics, you do the left-hand side. You try to model the forces, the actions that are exerted on that particular particle. So kinematics is what gives you the right-hand side of that. It's absolutely necessary to be able to represent the motion of a particle to the geometrical part of motion. Otherwise, you don't have this side of the equation, and you don't find any equations of motion. Okay. The other piece of information that we want is, well, we live in this space. We use these tools to represent what's going on, and we're talking about particles, and we'll do that for the most of the class. The other piece of information is that we do Newtonian mechanics. Do you know what that means? It's stuff that you should have done for 4 years now. So many different classes. You can guess. Newton's laws, but those are valid with the assumption that there is one and only one independent variable for everything that is happening around us. So I'm moving around. This is the phenomena that you're observing. I'm moving. I'm going back and forth. There is just one thing that is changing independently from everything else. Time. Time is the independent variable in Newtonian mechanics. Let me just abbreviate here. Independent variable. What that means is that it doesn't matter who the observer is. If I am looking at something moving, or if you are looking at something moving, if you are on a plane traveling and you're looking at something moving, the time ticks at the same rate, which is not true when you get close to the speed of light, as we may know. But even though satellites in low Earth orbits go to 7-8 kilometers per second, that's still pretty small compared to the speed of light. So as far as we are concerned, time is the independent variable, which means the following. That time for a given observer A is the same as time seen by another observer B. It's basically the same for any observer. And from this point on, this left superscript will indicate who is the observer. We're going to elaborate a little bit more. So far, what I've used is the underline for vectors and this left superscript just to say who is the observer. So these are really the key ingredients. Now, if you want to start from here to tell me what a particle is, so that you can take the time derivative once and you have the velocity, and then another time and you have the acceleration, well, what do you need to give me? Before the coordinate system. So this is one of those things where I don't like your book too much. I think it's a great book. But this first chapter confuses the concept of reference frame and coordinate system a little too much, which is something that we all do, most of people do, but they are two very different concepts. So it should be obvious that the observer matters, okay? If you're driving in a car 70 miles an hour and you're next to another car at 70 miles an hour, you see no velocity, right? You measure 0. If you're standing on the road, you see those 70 miles an hour. So the observer does matter for what you can measure. So the first thing we need to introduce is the concept that observers can be different. And that is the concept of reference frame. So we need to define what reference frames are. And these are not coordinate systems. So you all raised your hand saying that you've taken dynamics in this department, and most of you probably with Dr. Rao, but even with other faculty, you should have a clear understanding of what is the difference between a reference frame and a coordinate system, and why a reference frame comes first. Then once you choose a reference frame, you can define a coordinate system. How is that going, by the way? Moving too much?
That's fine.
I tend to move around, I know. I have too much space here.
I'll work with it. I'll figure it out.
Okay. You want to guess what is a reference frame? Well, I'll give you the definition, but this definition is not going to be the rigorous one to begin with. They are basically perspectives from which we observe, well, motion. That's what we care about. Motion of things, particles, again. What is a common reference frame that you are forced to use all the time?
The ground.
The ground, what does that mean? This planet. We're stuck to this planet, right? If you want, yes?
Within our own eyes, that's our reference frame, like what we can see.
Yeah, but the perspective is something you have to be stuck with. So say that you're running an experiment on this table. Would you be moving around, running around the table while you're running the experiment, you're taking your measurements? Would that be a good idea? No. So in this case, if my experiment, my small experiment, whatever that is on this table, this is my reference frame. I am looking at things from the perspective of this table, or definitely I'm going to be fixed with this table. I'm not going to move around the table. So they are perspectives, but there is a much more rigorous definition, which is the following. It's a reference frame is a set of at least 3 non-collinear points, of course, in E3. Everything we do now is in E3, whose mutual distances are constant. Okay? 1, 2, and 3. As long as I don't change the distance, this board is a reference frame. The ground is a reference frame. The table is a reference frame. Something else that we define in a very similar way is a rigid body. So as long as you don't really care about these objects having mass or not, you can call a reference frame a rigid body and vice versa. And they are usually actual objects. Again, we're stuck to this planet. When you're taking measurements of satellites that are going around you, or you're looking at a plane and you're saying it's going now north, south, or whatever that is, you don't usually run around while you're taking measurements. I don't think it's a good idea. So this is a reference frame. This is the formal definition of a reference frame. You choose some object and you glue yourself to that object. So an additional statement that I want to give you is finally an observer. What is an observer? Is a person, of course. An observer must be fixed in a reference frame. You don't move around if you decide that that's your point of view. If the board is my reference frame, I attach myself to the board and I don't move. It would be insane to take measurements of whatever is happening around me without having a fixed point of view. Now, going back to the comment, the eyes can be one. Yeah, this is a formal definition of a reference frame, but does it give me a way to measure anything? It just tells me that I'm sitting on the floor and I look at the world around me, but again, if I want to say where Patrick is with respect to my position, I need to give you some rulers to define the vector that connects us, right? That is a coordinate system. The coordinate systems are your rulers once you define the reference frame. And I'm going to define coordinate systems, but is this difference clear? I use, I don't think I need this anymore. Say that I'm using this third of the board as my reference frame. This is my point of view. Well, I will have to decide that I start measuring things from here, and this is one of the directions that I define in 3D Euclidean space, call it the EX direction. Maybe this is another direction, and they may lay both on the board, and then maybe something is sticking out and is my third direction here. And I need an origin somewhere. Now you can measure stuff. Now you can say that object is a such distance from the origin in that direction. Now you have everything. You have the object that is your point of view, and you decide from which point you start measuring positions. Is this clear? Now, let's be a little more formal here with coordinate systems. So that is, told at the beginning, I'm a big fan of dynamics. So if you come to me and tell me that a reference frame is a coordinate system and vice versa, I'm not going to like that. This is a reference frame. It's a set or collection of at least 3 non-collinear points whose mutual distances do not change with time. That is the only one that I'm going to accept. So in principle, as you solve problems, you need to tell me what the reference frame is. And usually these reference frames have infinite points. This board has definitely more than 3. But you need at least 3. Okay. So what do we do with coordinate systems usually? And this is small again. Sorry. Is this readable?
Yeah.
Okay. So now a coordinate system can be whatever you want. Now let's start talking about vectors just to warm up about them as we'll use them a lot. No, I'm sure you've been used to seeing things this way, that you have a vector and then these 3 little vectors here, E1, E2, and E3, and you say that E1, E2, and E3 is what? What do we call this? If I tell you that this is my vector B, I know it's pretty small, but hopefully you can see it. This is my vector B, and it's sitting here in 3D Euclidean space, right? And it cannot care less about who the observer is. It exists. No matter where you look at it, how you're looking at it, it exists. Now at some point you decide to use this representation. This is the representation of B. It's not B. It's one possible way of calling B. The same way I pick up a pen and I call it penna, boligrafo, whatever is your language. You can call it in different ways. It's still something you used to write. Doesn't change the nature of the vector. So if I do something like this, though, if I represent it this way, what does this need to be? It's a basis for E3, right? A basis for E3, which means that E1, E2, and E3 are what? No. They're linearly independent, right? So as long as they can span E3, you're fine. So you could have, in principle, coordinate systems that are like this. You can do whatever you want. If it's convenient, it's usually not. But, so, coordinate systems are basically something that require an origin. I'm going to write it down. An origin and a basis. You know, the 3 directions that allow you to cover 3-dimensional space. But what do we do usually? Well, we do the following choices just because we make the following choices because they make our life easier. We do what you were saying before. 1, I'm not going to choose these vectors to be at weird angles. So usually we say that EY dotted with EJ is 0 for I different from J. And I, of course, and J go from 1 to 3. This is the dot product between 2 vectors, by the way. This is the time to ask me all sorts of questions, because then we're going to move on, and I'm going to assume that you know how to do dot products and cross products and all that fun stuff that we do with vectors. So speak up. Now, and is a dot product or inner product in E3, which is going to give me a scalar. Okay, that's why there is no underline. If the result of this operation was a zero vector, I will have the underline even for the zero, of course. So that's the first choice we have, and then we say, well, I think it's pretty inconvenient to have these vectors of different lengths. I'm going to choose that they are all 1, so unit vectors, right? Okay, so they are normal to each other. They have magnitude 1, so that's an orthonormal basis. What is missing? Right-handed. Someone decided a long time ago that right-handed was convenient. You can do left-handed. You can do whatever you want. This just removes the ambiguity. We just agreed a long time ago that we're going to do right-handed. Now, I cannot do this. I'm really terrible to do the right-handed test to verify that I'm defining things correctly. What I do is this other little trick that is also in your dynamics book. You put the vectors that you have chosen as your basis in a clockwise order, the same you do with little arrows. And so if you go in this way, it's a plus for the cross product. So as you build your basis, E1 cross E2 is E3, E3 cross E1 is E2. If you go the other way, you get minuses. E3 cross E2 is minus E1, and so on and so forth. Believe me, I do that all the time. Every time I have to prepare a test for dynamics, and maybe for this class, I will have a little piece of paper with that, because I make mistakes. And this is really one of those mistakes that it's not worth making. So just apply some little tricks like this, and don't waste brain cells. So I'm almost done. I have defined 3 directions in space that are orthonormal and right-handed. What is missing here? Well, you have to choose an origin, right? So actually, you may want to do that as point 0 in defining your coordinate system. Let me say 0. Pick an origin. Okay? So when you're solving problems that have to do with dynamics, where you end up writing F equal ma, the first thing you do is that you define reference frames. It may be more than one. You define the appropriate coordinate systems, and then you start writing down vectors, positions, and take the time derivatives, which is what we're going to do. Now, what am I missing here? Say that I've chosen my reference frame. I'm going to measure things from a certain reference frame that I call A. And then I want to define the coordinate system. Can I do, for example, anything I want for this origin here? It's a point, right? The origin is a point. What should I say on top of pick a point? Fixed in A. In the chosen reference frame. It's what I said before. If my table is my reference frame, I'm not going to run around the table like crazy. I'm not going to move the ruler as I'm measuring something, because I don't think it's easy to measure something doing this, right? So you pick an origin that is fixed, and the basis also will be fixed. So I think now we have enough ingredients. Let me just remove stuff around here. To solve one of the problems that I gave that in the dynamics class, and I was mentioning to you the other day. I'll do it again. I don't think we solved this. I mentioned this, but we never solved it. So say that my reference frame is the board. And so you have to find these 3 points that don't change distances with respect to each other. And so now you have the reference frame, but you need to define the coordinate system that you're going to use. Well, pick an origin. Say that origin is 1. Is point 1. Okay. And what is missing is now defining these directions. What do you do? So I'm your customer. I come to you and I say, hey, I have this board and I have 3 dots here. Can you come up with a coordinate system? Because I don't know how to do it. What do you do?
You take the first
Ah, you looked at the solution? I hope not. I said, have you looked at the solution? No, just kidding. Yeah, first vector from 1 to 2.
1 to 2.
Yep.
That's your E1.
That's your E1.
Your E2 will be 1 to 2 crossed with 1 to 3.
Okay. For example, so I'm not going to call this anything. I'll call it A. So I'm going to cross this with this, and it gets me out of the page. And we're going to say that that's E3. Okay.
And then your final one would be
E3 crossing with E1.
E3 crossed with 1. Yeah.
So that's more or less what you would do formally. I would say E1 is what? Is the vector that goes from 1 to 2. Let's call it 1, 2. Normalized, of course, because I need unit vectors. Then I'm going to define A as, I don't even need to normalize that for now. I'm going to define it as the vector that goes from 1 to 3, whatever the length of that is, whatever the magnitude of that is. I'm going to do the cross product that was suggested to get out of the board. E3 is going to give me, E3 is going to be given by E1 cross with A. That gets me out and coming, pointing at you. But I need to normalize this because I want everything unit vectors. Okay? So I already have these two taken care of, and then E2 is going to be crossing those two vectors, and I don't have to do anything else because they are already unit vectors at 90 degrees. Make sense? This was 20 points. Took us 10 seconds. So I need you to be able to play with vectors, without being scared, because that's what we're going to do. All right, so we have coordinate systems, reference frame coordinate systems. Let's start talking about velocities and accelerations. That's what we need for kinematics. Now, if we're doing Newtonian mechanics, time is the independent variable. That means we start taking derivatives with respect to that t with no fear. If I have a scalar, say let y of t be a scalar function of time, we know that d dt of y of t is, well, whatever is the definition of derivative, which we never really apply. We have all those tables, but that's what it is. And I can take this rate of change without thinking twice. I don't have to tell you who is taking the rate of change. If it's observer A or observer B, say that I am A, you're B, and I am moving around and you're sitting down. It doesn't change. The pressure in this room doesn't really change. If you take its rate of change, it's independent from the observer, right? If I have a vector, instead, this is a small vector. Let me use my bottle here. This is my vector now. Now, if this vector is doing this, I see it changing. You do as well, right? If I go with a vector, I do not see it changing. You do. So the rate of change of a vector does depend on who is taking the rate of change. Make sense? As the example of the car. So vectors are a lot more difficult. So if B is a vector in E3, the d dt in B with respect to an observer A, so from now on, rate of change of something with respect to this reference frame is what I mean by these symbols here. Does it make sense? So this is taken by observer A. It's in principle different from the rate of change of B by observer B, who's someone else. So observer A is stuck to this board and observer B is stuck to something else that may be moving with respect to the board. So as many of you may be guessing at this point, what I need to refresh is the key result of kinematics, without which you have really no hope to do any mechanics, which is the transport theorem. So Do we all know the transport theorem? Kind of, I hope. Some people give this result here as almost like the magic formula. This, I'm not going to demonstrate it. It's on the videos on my website from the dynamics class. But this is something that can be demonstrated. It's not that hard, actually, but it is not a magic formula. So let's do this. Let B equal to B1 E1 plus B2 E2 plus B3 E3 B. What is this? This is the representation of B in this basis. And say that for now, this basis is fixed in A. A is a reference frame. Okay? So those are the axes, the directions that I picked in my reference frame A. And say that I want to take the rate of change of B with respect to A. So what is this going to be? The rate of change of vector B with respect to the observer A is going to be, you want to help me? Now, this is the basis for E3 that I picked in A, and these functions B1, B2, B3 that may change with time are scalars, right? The scalars, they're the projections of B on those directions. So this is dB1 dt E1 plus dB2 dt E2 plus dB3 dt E3. Anything else? No omega. E1, E2, E3 is fixed in A. So if it's A that is taking this rate of change, that guy there, that it's glued to A, doesn't see E1 and E2 and E3 changing. That's fine. In many problems, we can write a vector in a coordinate system which is fixed in the reference frame when we're going to take the rate of change. But unfortunately, that is not always the case. Example for this class. We want to send a satellite to Mars or some other planet. And so at some point, as we'll see, we want to know how that object is moving with respect to the sun for most of the travel until it reaches the sphere influence of the other planet. So in between sphere influence of this planet and the next one, mostly is affected by the sun. So we would like to know how it's moving with respect to the sun. I don't think that any of us can sit on the sun and start taking measurements from the sun, right? We cannot do that. But we still want to know how that object is moving with respect to the sun. So we want rates of change of positions and other things with respect to an observer fixed in the sun, which doesn't exist. Well, with the transport theorem, you still can do that because you know how the sun moves with respect to the Earth. So you take your measurements here, and you're able to say how that object is moving with respect to the sun, which is what we're going to do now. So let's say that now it's an extremely powerful result. The transport theorem is great. So let's say now, let's have E1, E2, and E3 is now fixed, not in A, is fixed in B. But I still want that d dt of B in A, but I am writing the vector this way. So now I'm able to write the vector in a basis which is fixed in B, but I don't care what B sees necessarily. I want to know what A sees. Again, A could be us, and B could be the sun. Sorry about that, the opposite. B could be us, and A is the sun. Is the observer that we don't have. Well, the transport theorem tells me that, if you want, we can do a few extra steps. What you will have to do is the following. dt ddt of B in A is going to be that portion there now, three plus, now we have these derivatives, right? Plus B2, and this is not B, this is E. Okay? So now A does see those vectors changing. The basis, now it's fixed in B, right? If we have time, I'm going to start a small, simple exercise. I don't know, otherwise we'll do it next time. So without demonstrating anything, this formula ends up giving you something much nicer, of course. What is this? What are those first three terms? You can stop me if this is not clear, okay? I see people smiling, I see people crying. I don't see anyone sleeping, so that's okay. Yes?
Should there be reference frame A's in front of...
Yeah, sorry, yeah. Yeah, absolutely. Thank you. Yep. If you have a rate of change of a vector without telling me who's the person taking the rate of change, that's something is wrong. So that's what B sees, right? Because B has these guys fixed. So this is the rate of change of B according to observer big B, capital B, right? That guy doesn't see anything else. The second part, which is not something we're going to demonstrate, all the rest is the difference, of course, because this is what A sees, this is what B sees as the rate of change. The rest, we're not going to demonstrate that, is omega of the angular velocity of B with respect to A crossed with B itself. So this is your transport theorem. If I am an observer fixed in B, but I want to know how, and I can write the vector little, small b in my coordinate system, but I want to know what A sees, as long as I know how the two reference frames, B and A, move with respect to each other, I can find the rate of change of B in A. Yes?
I'm sorry, just to understand your nomenclature, that is the angular velocity of B with respect to A?
This is the angular velocity of reference frame B with respect to A. That gives me the information, of how B is changing orientation with respect to A. And in fact, it's carrying the information of how these little guys here, E1, E2, and E3, are changing as seen by A. If you are the observer A and B is the board, and I remove it from the wall and I get arrested for that, and I start moving it around, you start seeing those little e's that are glued, that are lines that you draw on that board. You see them moving, right? So that's your piece of information here. Now, again, here we don't demonstrate stuff, but we summarize the key results. What is that angular velocity? The angular velocity has interesting properties. Is not a theta dot only. It is for single axis rotation. For three-dimensional rotations, we can bring things down to that. And when we need Euler angles, for example, we'll do it. But for a single axis rotation, say that you have this basis here that is fixed in this is fixed in A, right? And then the little e's are the basis that is, so big E3 and little e3 correspond to each other. And there is a single axis rotation. We represent this rotation by an angle theta. In this case, in this single axis case, the angular velocity of B, so this is fixed in B, with respect to A is theta dot little e3 or big E3, doesn't matter. But that's a special case. Things don't usually move rotating about a single axis, right? But we can bring down everything to single axis rotations. We can decompose rotations that way, because we have the following properties that are valid. The first one is the chain rule, which tells me that the angular velocity of a reference frame C with respect to A can be decomposed in the following way. C with respect to some intermediate reference frame B, and then B with respect to A. So you basically go from C to B, B to A, here it is, C to A. And if you have more than 3 reference frames, this keeps going. So if you have these reference frames, objects, that rotate with respect to each other, you can do this. You can apply the chain rule. We're not going to do that now, but this property will allow me to bring down 3-dimensional complete rotations into single axis rotations about intermediate axis. I don't know how many of you have seen formally and completely other angles. Many, probably. So that's what you do. You bring down everything to single axis rotations, and so you're done. So all you need to remember is that, yeah, this is true for a single axis, and then a generic rotation can be decomposed into particular single axis rotations. That's the first property. 2 is that the angular velocity of B with respect to A is also equal to minus the angular velocity of A with respect to B. Can be useful. And another one is that the angular acceleration of B with respect to A is the rate of change of omega, of course, of B with respect to A, and does not need the observer. This is one of the few cases. There is a simple way to demonstrate that. If you want, you can come to office hours and I'll show it to you. But the rate of change of the angular velocity can be taken by anyone. It's going to be the same. So these are the things we need to remember. Maybe something else that I may have forgotten that I have in my notes. Let me see. Before I start showing a very simple problem. So what is the point of having the transport theorem, as I said, is the fact that in many cases you may not be able to write the vector B in a coordinate system which is fixed in A. Because if you were able to do that, then you would only take the rate of change of the scalar parts, right? Like I did at the beginning. You don't have to take the rate of change of the little unit vectors. But in many cases, you cannot. The example that I gave you before. Interplanetary travel, you really cannot do that. So, but you know how the sun moves with respect to the Earth. So you know this omega of sun with respect to Earth, for example. So you can compute velocities and accelerations of your satellite with respect to the sun, even though you're measuring its velocities and accelerations with respect to the planet Earth. So it's a very powerful tool. You can basically tell me what an alien on the sun sees, as long as you know how the sun moves with respect to the Earth. So you can take your measurements down here. You don't have to go there. It's a very powerful tool. On top of that, there may be cases where you can actually write B in a basis fixed in A, but that vector ends up being so ugly that when you start taking the rates of change of the scalar parts, they become monstrosities, and you lose track of what you are doing, and you don't have any insight in terms of the final result. So I think I've really talked enough today, and we're almost done with kinematics. I want to start showing a simple problem that is an application of transport theorem. It's a standard dynamics problem. But we started here, maybe we finish it next time, maybe you guys finish it. So I have the ground, say that it's the floor of this room. This doesn't have anything to do with space. We're going to look at gravitational forces in a couple of lectures. So no space for now. And I have some type of pipe, I don't know, a straw, whatever, that it's rotating about this axis that is normal to the board. And there is a small particle here that can move inside the straw. And I represent this rotation with an angle theta. And I call this the ground. This is a reference frame, the ground. And I call this distance between O and the particle up there, O and P, I call this little r. And I want velocity of, so let's start understand the nomenclature here. V is a vector, so underline vector. I want the velocity of P. I could write the subscript here, but there is only one particle, so let's not do that. I want the velocity of P with respect to the ground, which is the rate of change of the position of that which is a vector, with respect to G. That's what I have to do. So if this was a dynamics class, I would expect for you to tell me that the reference frames, and it's always good to do it, are two here involved that you may want to use. One is the ground, one is that arm, call it A, this object here, right? Rule of thumb is that if you have one rotation, you probably want to define two reference frames. Any additional rotation, you add another reference frame. That's the rule of thumb. Two reference frames, and then you have to define the coordinate systems. And you define one which is fixed to the ground, has an origin in O, as an axis EX, for example, that points this way. I'm not going to waste too much time here. EY, we don't have too much time. EZ sticking out of the page. And then you have to do the same for the arm. I will probably pick, so this is, the origin at O is good for both of them. Why is the origin at O good for both of reference frames? Yes? It's a fixed point in both reference frames. That point O doesn't change with respect to the ground and with respect to this rotating pipe here. And so for A, we'll probably define some EX direction this way, and an EY direction this way, and an EZ that is sticking out of the page. And so you've done reference frames or coordinate systems. You can start writing vectors, right? What is R? I have to start from there. I have to start from the position so that I can take its rate of change. You can write that in multiple ways. Two ways in this case. You can say that it's R EX. You can also say that it's R cos theta big EX plus R sine theta big EY. Now if I want the velocity of that particle to begin with, then we'll do the acceleration. With respect to the ground, what is your temptation here? What would you do with this vector R? Yes.
I have a quick question.
Yeah.
What's your origin for the small e?
The same. So origin is for both. Yeah, I'm going a little too fast, I know. We'll pick it up next time. Again. So what do you want to do? What would be an idea here? This is how the gentleman here, or the lady here, that is fixed to the ground, sees that point moving. It's the velocity that this guy measures, not the guy that is sitting on the pipe, of course, because I put the G here, right? So for this guy, big EX and big EY do not change. So the temptation is, which you can do, is take this expression and take its rate of change directly, which means that this is not going to change, this is not going to change, you just do the scalar parts. So do it that way, and then take another rate of change, and that gives you the acceleration. Then you do the following, you use the transport theorem. You use this expression here, so you write that vector with respect to the basis that is fixed in A, and you use the transport theorem. So you have to define the angular velocity of A with respect to the ground, and you will see how much nicer the calculation will be. So you have a gain in calculation simplicity, and the result that you will see will show you a radial velocity and a tangential velocity, which you do not see when you do it from here. So the transport theorem is not just because sometimes you cannot write the vector in the basis you want, even when you can. And this is a simple problem, by the way. Who cares about a pipe that goes around with a ball inside, really? No one. But even when you can, it just may not be convenient because you get expressions that don't give you any insight. So I am all about transport theorem. When I can use it, I use it. And that's what I suggest you to do, and we'll do. I think we need to stop here. I'll see you on Monday. Have a good weekend.